I've been running and trying to catch a taxi. I learned a lot about Edinburgh, as you said. So, yeah, my apologies for being late. Um, I I went to the wrong spot. I trusted myself too much, and then I realized I'm all wrong. I got the wrong spot. Um, so, I'd like to thank Professor John Boy and Professor Ngubak Cho for this opportunity to be here, for this to be part of this wonderful meeting. So I'm going to talk about statistics and probability, and some Vietnamese snapshots. So of course, statistics and probability is a big field, and it's presumptuous of me to talk about a lot about that. But the community for Vietnamese researchers in this area is still very small, despite there's a lot of interest. And I'm trying to just give a sort of impressionistic sketch of this area, and then I point out where there's some of the interesting work by Vietnamese researchers, and I would highlight some of the work that, for those who are present, that they're going to talk later on Tuesday. As I said, statistics and probabilities is a huge area, but the interesting thing about this, as you can guess, is that any researchers in this area, they will get some kind of data. So the way for me to think about sort of the landscape of this area is to think about what data, what kind of data that someone is working with, and what they're going to do about that. Like, in particular, the kind of data that statistics and probability researchers working on, they have very close connection to the real world applications, even though they can work on abstract objects and so on. So data is what I talk about, and I thought I should show you this quick sort of my own data, kind of snapshots that I have collected over the summer. It's data and data. When I think about this, is I visited Vietnam in summer, organized a summer school, organized by, sponsored by VIASM and University of Economics in Ho Chi Minh City. And when I think about data, I think about Vietnam, I think about a lot of data, a lot of activities going on. You see some traffic, cannot avoid it. A lot of color and sight and sound. And this interesting picture, I also visit my old hometown, and this is I took a picture of my cousin who's a teacher in literature, giving their this is the high school students taking some training in her house, and of course a lot of people, a lot of interactions, and the last sort of bunch of pictures here show the activities in the Bayesian summer school in Ho Chi Minh City. This is the hotel that we went to. So yeah, a lot of data, a lot of time to observe them, not a lot of time to think about what's going on. What does it mean? So yeah, so when we think about the data and talk to a particular researcher, you can ask. So for instance, somebody working in physics, they are interested in data of the very large scale, right? The kind of observations about stars and galaxy and so on, and they're trying to understand the origin of the universe. But the data could also be a very small scale. For example, if you can observe the evolution of the cell populations or cellular or molecular levels, and you can try and understanding something like the effects of aging or cause of disease, and based on that understanding, one can design a new drugs, medicine. So in fact, Hoàng Văn Hà going to talk a bit about is researchers motivated from this kind of data. Social science, etc. Engineering, you saw the kind of traffic, and now there's a lot of technology that allows you to collect a lot of through sensors and camera. You have a lot of these observations, and if you are someone who work in the sort of controlling the traffic, you want to use that information to improve the flow of the traffic, or people interested in improving the safety of their car driving, right? Or even those who want to build semi or fully automated car driving. And in these days, of course, part of the reason we have so much data around is is the kind of information or data that are generated by mobile devices. Right? Everybody has the mobile phone. They use that to connect with other people. A lot of connectivities. So you have this kind of media content generated from that. So you might be interested in, if that is the kind of data you work with, you might be interested in, say, detection of community. And you cannot avoid any talk without nowadays about generative AI, where what kind of data they work with? Well, they develop algorithms operated on a lot of say text images. That's their data. But what for? What their quantity of interest? We still don't quite know. Maybe generated more images or more text or something else. So that is still the process of thinking about, here's the kind of data you're interested in, and what is it that is your quantity of interest. And I use X for the data and theta as a Greek symbol for the quantity of interest, but even that can change as well. So you see, what's interesting about data is the role of randomness, right? It's a way to control, to capture the complexity of the variation in the data, things that you know only up to a degree, and then you make assumption about the randomness. So that is where the role of probability comes in. Obviously, we assume data to be sample of some random variable X from some unknown probability distribution, denoted by this P sub theta dx. So theta, now you can allow theta to play the role of parameters. So suppose that somebody working with network type of data, then that they have to abstract that away. They would think about things like random matrices, random graphs, and this is the kind of researcher that that I'm aware of that working on this area, and Ken is going to talk about his work tomorrow as well. Other kind of random discrete structures. When you think about the kind of traffic type of data collected over time, there's some kind of smoothness patterns. So you think about random functions, stochastic processes, and so on. And if you want to be fancy, you can also talk about distributions, but random distributions, especially if you work in Bayesian statistics and so on. Right. So that is about data, right? So that's your X. And different researchers work with this different kind of data structures and different notion of randomness on those structures. And really, you can ask, what is it that they're trying to do with that? What is the quantity of interest? So if you are a mathematician, say if you're looking at probability, right, the usual kind of quantity of interest would be some quantities about the probability distribution that is achieved by proving some limiting theorems about, that is, about the empirical samples, right? So probability 101, right, that any undergraduate student know is you take, let's say you have an IID sample from some probability measure P on some space X. Then under some conditions, then you take the empirical average, then that will tend in the limit to the expectation of that distribution. Defined this way, conversions can be defined in suitable sense, provided that the left-hand side and the right-hand side are well defined. And you can have a refinement of this kind of result, like central limit theorem, which is with the proper scaling, right? You take one of a square root n here, say, and of the sum of this sample, then it converts in distribution to the Gaussian variable. So that we all know. So what is the modern themes? That's all about extension of this kind of basic phenomenon, basic fact. So for example, if the X here, your data X, now represent a sample from a random matrix or a random function, then all these observations, they are no longer independent. Right? They might not be even identically distributed. So there's the work to do about that, and moreover, you might require more sophisticated statistic than the usual kind of empirical average in order to actually define to define a meaningful quantity on the left hand side here based on the data. Right, so you'll be interested in things like central limit theorem for random matrices, classical result like Wigner's semicircle law or Pachenko-Pastur theorem, but a lot of works that will extend this sort of central limit theorem type result in various structure. And as I said, you need other kind of statistics or functionals on random objects, especially when these kind of observations, they no longer live in sort of standard vector space. You can take the average and try to make sense of it. Maybe it doesn't make any sense that you actually about the distribution you care about. So one of the very common theme in modern statistical probability is this precisely situation. And I will illustrate with some example that often you don't actually have an explicit statistic that you can define on the data. Rather, they have to be taken as output of some algorithm, using the data as input, and yet you're trying to make use of those kind of output, that you obtain from the data that coming in through some kind of algorithm, and so for that you need, what kind of statistic would be relevant? You need some kind of model, underlying mathematical model for that, and the kind of central limit theorem that we might look for, they become the kind of Bernstein-von Mises type theorem. That's some sort of thing that Julie is so expert in. So in this conference, we'll hear some of this work of this sort by Ha, by New, by Can, about some kind of limiting behavior of various types of statistics that are either explicitly defined or implicitly defined. So let me give you a sort of example of the kind of implicit statistic that still you want to understanding the behavior, because those are the kind of statistics that are useful. So this draw from my own research interest. Working with some astrophysics collaborators, that they trying to they collect information about the Orion Nebula. So this is an interesting part of the this in the sky map, that there's a lot of activities going on here. This is considered to be a nursery of where a lot of stars being born, and now we can collect this data, this information by through some X-ray measurements collected by the Chandra Observatory. So if you can actually visualize the kind of observation, it looks something like this. These are the position where you detect something that is attributed to the photon source. Okay, so this is what you see, position on the sky map, and so you can treat that as your observations, right? And you say, well, I can assume that these are IID sample, or these observations, IID sample from some kind of mixture distribution that has this form of density. So it's just a convex combination, sum over Pj times some kind of kernel density F that you applied on the X position on the sky map. And there's some parameterization for each of these kernel density function theta. So theta j here might represent, some kind of information about each of these cluster of the photon source. So it might be saying something about the arrival time of the location where there's this event that you can actually now observe. What is the energy level of this photon source? So this is actually the kind of model that astrophysicists are using. So you see, the data that you observe are this kind of measurement from this kind of X-ray measurement. But you want to turn that into, you have to devise some kind of algorithm based on this model that allows us to make inference to say something about all these parameters theta j, which is say a lot about the what's going on in Orion or Nebula. So this kind of statistics is not obvious. Right? So for those who know, you have to apply some kind of algorithm like the EM algorithm, expectation maximization, or you apply the Bayesian type of method where you have to approximate, you have to simulate from the distribution, the posterior distribution, in order to do inference about this kind of parameter. So in general, the kind of quantity of interest that a lot of probabilists and statisticians are interested in is just to construct probability models and compute those distributions for complex random objects. So what are the classical examples? We already know about Wiener process, random motions, or Gaussian measures, Markov chain, Markov processes, random measures. You want to talk about process in continuous time. There's notion of stochastic integrals, or in various applications, it might be easier to think about the process you're interested in as a solution of some stochastic differential equations. So the modern themes seem to me that it's all about sort of extending all these tools to develop more complex processes, because the data are just getting more complex, more complicated, just because our ability to collect more of them, more different types. So we need more complex models for that, especially extending in multi-dimensions and nonlinear setting. And once you do that, most of the kind of quantities you're interested in are not easily available in explicit form. So the common challenges then is that we need to approximate by some algorithms to obtain. So for example, you can study certain kind of solution for certain stochastic differential equations, but you cannot have access to those processes in explicit way. You need to develop numerical approximation of those, and Nguyen Long is going to talk about that. Or as I mentioned earlier in the previous example about the actual physics data, you're interested in distribution of the theta that you're interested in, and you cannot really compute them exactly. Then the usual way people do could be to simulate a Markov chain and in the limit to the kind of distribution of interest. How to construct those kind of Markov chain that have a very nice mixing property. And another kind of example is to model distributions of data that are concentrated on manifolds, lower dimensional manifolds in high dimensional space, based on push force measure. This is what have been used a lot in the past 5-10 years. That often, you can take a very simple property measures, something that nowhere else even the Gaussian measure, push forward that through complicated push force maps, and then you can really approximate anything. And that is the kind of technologies that people use these days for in machine learning, in generative AI models for images and text. This push force map, they just feed it with humongous neural networks, and they do a lot of optimization to learn the parameters from those. Turns out to be very effective in those type of applications. So in modern times, the interest might not always be about the underlying distribution of that is captured by the parameter theta. That we often use the Greek symbol for what we're interested in. So, but rather in a lot of applications these days, people are more interested in the prediction of unseen samples. So I use italic X or Y for that. So that also represents a shift in the kind of focus among a lot of research. So to make it easy, let me talk about some simple standard problems. So supervised learning. If you have an IID sample of the pairs of X and Y from some unknown distribution, and the goal is to find a classifier F that is applied on the X space that minimizes the misclassification error. So you can apply to the input X, you're trying to predict Y. So modern application would be, say, X would be a bunch of photo images, and Y would just be the people's names. Or, is that a dog picture, the cat picture? But now, you go to the airport, right? You go to the visa, they take your photo and they can verify if that's you or not. So that's very, very impressive use of this type of data-driven technology. If Y is a continuous space, then the problem is called regression problem, which is, for me, is kind of a misnomer, because in the old days, right, when you're interested in understanding the theta parameter, trying to express Y in terms of X, then you're trying to regress Y to X. So that's why you use regression. But in a lot of modern application of regression, you don't really care so much about the parameter. You want to predict for the new sample of X, for the unseen sample X, how well can I estimate Y? How well can I predict the Y that is associated with X? So you're trying to minimize this kind of mean squared type error. So that is also represent a shift in the interest. Unsupervised learning or generative modeling is a kind of things where you don't have the Y, the response Y. You just have a bunch of X data from, you assume them to be IID sample from some unknown distribution P. And you try to, in the old days, right, the standard, the classical way is just trying to learn a distribution that can represent this sample as well as possible. But with modern kind of application tend to be, well, I want to generate more X tilde from the P tilde that looks more and more like the integer sample. So this is the kind of application in say, generative AI type where you have an sample, right? You want to produce more X that looks more like those Xi. So how do you mathematically quantify what's going on? Well, essentially you try to do something like this. Right? You look at the empirical measure. This is the second argument that I wrote there, 1 over n, the sum over the data. Right? You look for the kind of a distribution P tilde. Now that can be parameterized in some complicated way. And you try to minimize some notion of distance between P tilde and this empirical measure. And I'm just using the kind of optimal transport type of metric, say W1. This is Stein, Katorovich, Rubinstein, which represent, which admits this this is sort of the dual form where you can evaluate this distance in terms of a class of test function in the Lipschitz, right? And then you can evaluate them, and you find the supremum among all those test function in this space. And so that requires to solve some kind of min-max problem. So that's the people in AI, they call this adversarial loss, minimax. But that is really what they're trying to do. This is a kind of loss of the kind of objective function that's interesting. Because I cannot talk about data approach without talking about Bayes and frequencies, because in almost any solution to the data-driven problem, you have to confine with whether you take a Bayesian approach or frequencies approach. Especially mentioned that we are staying here in this building under his name's Thomas Bayes, so let me just quickly say what it is. Let me see how I do with time. How much time do I have?
Say five minutes or so.
Okay. Here being in Edinburgh, Joe reminded me that David Hume was here, Scott, and he was here, and he was one of the first person who sort of asked the question, how can we sort of mathematically, now we phrase in modern language, formulate or formalism that can do inductive inference. Inductive inference mean from X, how can you say about theta? Theta may have nothing to do with X. And from his point of view, he concluded that theta has nothing to do with X. Theta might be, does God exist or something like that, right? But Bayes essentially perhaps the person who have to formulate one of the most general sort of framework and powerful framework that allows to actually ponder this possibility.
Oh, Laplace, actually.
Yeah, and then of course Judy pointed out that maybe it actually is Laplace. Yes, I say, not just Bayes, Laplace also. So let's consider this example. Let's say we have n IIDs, n samples, 0, 1 value that describe whether it's cloudy or sunny in Edinburgh. So the question would be, well, you have seen Edinburgh, you spent the first 6 days here, and you're going to be asked, what's the probability that it's going to be sunny on your final day? The frequentist solution use the usual notion of probability that we learned, the notion of the notion of probability as frequency. And the way it goes is following. Well, I'm going to assume that this n sample, n plus 1 IID, from a Bernoulli distribution with parameter theta, which represent the frequency, right, of sunny days. So, obviously, you're going to estimate theta using this empirical sample, right? You find the fraction, right, of sunny days, and then you say, oh, that would be the probability that it's going to be sunny on the last day. Now, if you actually have been in Edinburgh, which we have, it's kind of funny, kind of strange to actually assume that, oh, this X are IID. If the goal is to predict about Xn plus 1, doesn't make sense to think that this, of course, we can, maybe you can agree that X is random. So for a moment, right? And but it doesn't make sense to assume that they are independent from the past 6 days. If you've been here and then you see it's rainy all day, you would think that maybe perhaps xn+1 is rainy too. Very high probability, right? So that's a starting point. We can still assume, say, let's say assume you can agree or disagree, but we have to make some assumption. But doesn't make sense to assume independent, but we can assume that these variables are exchangeable, that they're dependent. They're somewhat dependent. And this assumption can be accomplished by assuming that all of these data, x1 up to xn+1, are conditionally IID given the parameter theta. So if you make theta random, right, then all of a sudden all these x variables actually become dependent, basically probabilistic dependent. And then you can put a distribution on theta, we call that a prior, and then what Bayes contribute is the Bayes formula, right, that allows you to compute the conditional probability of theta given what you have observed. Right? Use this Bayes rule, and you go from there. So this does require the notion of Bayesian probability, which is built on conditional probabilities, which is obviously a much more sophisticated notion of probability, but moreover, it doesn't quite have the same kind of frequency interpretation. Right? So that allows you to make mathematical sense of statements such as, what is the probability that Biden wins the US presidential election in 2024? Obviously, you can't use frequency interpretation in order to make sense of that statement. So once you sort of, so often in a lot of application, Bayes or frequency approaches, they don't produce different result. But in some application, like the last one I said, right, you can make a different in kind of result. Because inductive inference, right, requires some assumption that people can agree or disagree. From a computational standpoint, from the actual implementation standpoint, that you need to develop a method on the data. Often Bayes or frequentist approach, they have implication on the computation. So if you use frequentist approach, there's a lot of optimization involved, because often you don't care about the randomness of what you don't know. And, you just need to have a point estimate for the parameters. So you really need kind of large-scale optimization. That become a very central part of all statistical machine learning or AI type algorithms. Nguyen Long is one of the experts in this area. He couldn't come because of the time constraint. But you could be a good speaker for this meeting. With Bayes, you need to do a lot of Monte Carlo method because you need to approximate the entire distribution. And so for that, often the standard technique is to simulate the Markov chains for the to obtain the kind of approximate samples for the distribution of interest. So here are some of the experts in this area. Now, Nyat or Kuang, they gave talk at the Bayesian summer school in summer, so I won't talk too much about that. The last point I want to make about the role of computation, and this is really for me is quite fundamental. It's really quite I don't want to use the word, but paradigm changing. But at least for me, that's how I see it. Is that it's true that in the past, often algorithms they often play the front role, right? Especially because they operate on the data. You know that the data is out there, and there have to be some algorithm with computers, with software that operate on that with hardware. And so even in the media, you talk about algorithms. There's nothing we needed that is known. We all know that underlying there's always some mathematical models that drive all these algorithms. But what I think is quite interesting, is really interesting, is now I think algorithms are also increasingly used not just for estimating the underlying model's parameters, which is the classical way to think about it, but people also use algorithms to actually construct the modeling, and to use algorithm to really define the models. And that I think is new. So let me give you an example. It's fairly modern. So you take a standard stochastic differential equation, right? There's some drift term, right? And there's some diffusion here, just usual Gaussian noise, random and some simple drift. So apply this kind of process to, say, the original data, which is an image like this, a picture of a dog. you keep adding Gaussian noise to the pixel, which represent this image. Okay. And if you do that, there are various ways to do this, but if you add a little noise a little bit, eventually the image become more blur, right? And it's become more blur. By the way, the pixel here represented by just a number between 0 and 255. And it become blur and blur, and eventually it look like just a noisy picture, right? Just like you cannot distinguish of anything. So it just looked like kind of normal Gaussian kind of noise distribution. And yes, that's true that if you are judicious enough about this process, about F and G, then the limiting of this would be normal for certain type processes like Austin-Uhlenberg type of processes. So what it does, so this is a classical kind of result, but what it does is that the engineer, they look at this and they say, well, we also know that the SDE has a reverse process, right? If I can go from the picture of the dog to a noisy picture.
You won't see anything.
If I can go from the picture of the dots to a noisy picture that assumed to be from normal distribution, then perhaps I can go back. I just can go from the noise, the Gaussian noise, which doesn't contain much information, to the picture of the dog, right? So they use that kind of intuition to build a model for images. And in fact, in some sense, for text too. Right? So here's a reverse process. That's the reverse process of this forward process. And the game now is you generate according to this process, starting from just Gaussian noise. And of course, you need to learn this parameter that you parameterize for the drift and for the diffusion part. And of course, they put in the humongous neural networks to do that with a lot of data. So what it does now is that you do have a very complicated model with a lot of parameters, billions of them, or hundreds of billions of them, but that can approximate image at a very shocking degree of accuracy. So that is also a new trend that you see that somebody working on SDE like Nguyen Long or Ho An Han can totally do the kind of generative AI model if you're interested in that. There's also a lot of interesting sort of modern areas in the statistics which I don't talk about, partly because I don't really have experts in this area, but I also think very useful and relevant and influence about cause and effect. Sequential decision making, which allows you to make this kind of inference or prediction, one-shot prediction to integrate it into a sort of a more complicated setting. Game, this is where it has been used successfully. Protein folding structure design problem can be used is this kind of technology. Reinforcement learning with human in feedback loop. Yeah, this is where you start to use all these statistics based method, embed them into the real world in a much more sort of ambitious ways you are seeing. So yes, so actually I think I'm running out of time. I have a snapshot of 5 researchers. Perhaps I read their papers, and I think they if I can maybe say one sentence each, and then I will stop so that Judy can time. So tomorrow we're going to hear about from Peng Mai about regression with a twist. It's a sort of modern twist where the response Y now no longer live in the Euclidean space, but rather living on server. Okay, so she's going to talk about that, a very interesting work, and she's going to talk about both new method and theory for them. I'm going to talk about. I really like enjoy reading his paper where he talked about how to model or consider model the evolution of a cell population using SDE and trying to utilize the characterization of the limit of the solution of this SDE in terms of some partial differential equation. Use that understanding to turn that into a statistical problem that allows him to estimate the parameter that drive the evolution of the cell population. It's very, very fascinating. I think very modern work. Nguyen Long talked about how to approximate the stochastic differential equation, again, I also think very interesting in modern work because the kind of process that he works on is very interesting. It has real interesting application, non-colliding particles of evolution over time. There's some technical issues about how to model them. No explicit representation is available, so you need to come up with kind of semi-implicit, very, in a very similar center I mentioned earlier, because you have to solve some kind of optimization in order to provide these approximate to the process. So you're going to talk about that. You talk about a very general class of stochastic approximation learning algorithm that and trying to characterize the limit of this process. And it can come from a lot of machine learning type of algorithms. That turns out to be a special case of this. And finally, we'll talk about parametric bootstrap and random networks. So this go back to the earlier example about when the data are no longer living in a standard vector space or Euclidean vector space. So here you have a graph type of data. Yes, you trying to infer about this graph structure using some non-standard statistics. So what can you say? What can you do about that? So I think I should stop here. Thank you very much.
There's one thing.
Is there any